Welcome to your first lecture video in the summer assignment for AP Chemistry. This is going to be designed to kind of get you used to the way this works, as well as to give you some information from the summer assignment unit, the first topic, the first part, which is really the introduction to chemistry and scientific models. So make sure that you have already completed your own learning targets. You should have already in a learning target notebook a foundation for what you should be expecting in this video. I'm going to try not to duplicate a lot of the work that you've already done, but rather to try to build on it. So it's going to be really important that you have these completed before you begin. These are the same learning targets that you'll see for topic 1, part 1 on the learning targets of the summer assignment. So if you've already completed them, then you're ready to keep watching. If not, then pause the video here and make sure that you take care of this from your textbook first. And if you're ready to go, then you're ready to go on and add to them as you watch the lecture. So the beginning of this is to try to build some things for you that you'll be expecting as you're going through the year and expected of you on the AP exam. You'll notice that I'm not going to touch on a number of these learning targets because I think they're pretty straightforward, but I am going to touch on some things that I think will be important as you go and things that you may not have been able to pull out of the book on your own. I will also give you some examples. So the first thing that I really want to talk about here is not the very beginning of what you started with, but rather the idea of a macroscopic view versus the atomic or particle view. Your book calls it the atomic scale, but College Board talks about particle diagrams or drawing particle views of things. And so you'll be expected to be able to interpret as well as draw your own particle drawings on the AP exam in May. So some things that you'll have to be sure that you're careful about will be things like the relative sizes of particles. I'll talk about that with you in just a second. The distance between the particles. So notice definitely that in here, you can see how the solid, the particles are tightly packed. The liquid is that they're packed together, but they're not nearly as organized. And so the key here in the difference between these two is the organization. And then of course for gases, the particles are far, far apart. So this is something that you want to make sure you're aware of, far apart and disorganized. So the distance between the particles will be important. The location of the container as well. If you have a solid in a container, you would want to draw it on the bottom of the container rather than up here at the top somewhere, right? If you have a gas, it should be clear that it fills the entire container, etc. So you want to be careful about how that works. And then if you have a mixture of things in a container, you're going to need to, or if you have an ionic compound, you're going to need to make sure that you're orienting the particles relative to each other correctly. And this is usually based on the polarity or the geometry, etc., and the charges that particles might have. So you definitely want to make sure that you're paying attention to these things, and the more practice you give yourself during the year with particle drawings, the better you will be in May. And that is something that I think it's helpful for you to understand the concepts of the course, but it's also, we are training you to hopefully do well on the AP exam, which seems like a long ways away at this point. So let's look at a few examples of particle drawings that I pulled in from some different sources. And I want you to notice some of the things that I've already talked about with you. Notice that these two pictures here, this picture and these pictures, are pictures of solutions. Okay, so because, and I know this because this says this is sodium chloride in water, and I know this in the pictures with the flasks because they gave me molarities. And so I know that these are solutions. And in the picture of the sodium chloride, they included the water molecules. You can see them here, the little Mickey Mouses, okay? But in the pictures in the flasks, they did not include them. And so this will be important for you to be thinking about because there are times when we want to include them and College Board will ask you to draw them, draw at least this many and at least this many. But there are also times where they're not really relevant and we just are looking for the species that are in solution. Often this species in solution picture comes from the end of a limiting reactant question, etc. Okay, so some things that I definitely want you to notice is that we have the positive negative orientation up here in this image. And you can see that the polarity of the water molecule makes the hydrogen ends, these ends, positive, and the oxygen end then is the negative end, right? So you want to make sure that if you have sodium ions and chloride ions, that your chloride ions, which are negative, and your sodium ions, which are positive, have been pulled apart and been attracted to the water molecules the way that they would be. So you can see that the negative end of the water molecule has spun around so that it's closest to the positive ion of sodium, and that the positive end of the water molecule has spun around so that it's closest to the negative ion, the chloride ion, right? So this is important. If you have them just randomly in there, that doesn't help you to understand how the dissolution process works. But when something's dissolving, really you have to break the original attraction between the water molecules and each other, and the sodium and chloride ions to each other, and form new attractions, and the water kind of sneaks in between. So this picture definitely shows that. You also would want the correct number of ions. So notice that in this picture of these other solutions, potassium chloride is 1 to 1. So we have the same number. We have 2 potassium ions as we do chloride ions. We also can notice that in magnesium chloride, there are 2 chlorides for every magnesium. And so you can see that there are 4 chloride ions and only 2 magnesium 2+ ions. So these are definitely things that you want to take note of. Also notice that this solution of KCl is more concentrated. It's 0.2 molar, and this is 0.1 molar. So in the 0.1 molar picture, there should be half as many of each of the ions. And sure enough, in this one, there's 4 K pluses and 4 Cl minuses. So we definitely are paying attention to quantities and relationships and etc. Okay, we also are paying attention to particle spacing. In solutions, the particles are not tight packed together. So you can see that up here in the solid, up here at the top, in this copper carbonate, you can see that this is very neat and orderly and that the ions are tightly packed together. You can also see the charges. So you can see that the carbonate ion, which is bigger than a copper 2+ ion because it's multiple atoms in a polyatomic ion, is definitely oriented so that those carbonate ions are alternating with the copper 2 ions, right? So that the positives and the negatives are surrounding each other. So this is important in an ionic solid. You also want to notice that if we have a solution of a molecular substance like hydrofluoric acid, this is a weak acid, so you'll discover more about that as you're working in your summer assignment. But this is a weak acid which does not dissolve into ions, rather it dissolves into molecules. So if I had liquid HF, it would be F and H and F and H and F and H, etc. And they would be not super organized and kind of together a little bit so that you can see how this works. And they are polar, so they would be attracted as such, but all these molecules would be truly discrete molecules all attached together in a liquid format, right? Once we dissolve it in water, now those molecules stay molecules. They do not become individual ions like this up here did. And so that's important as well. So that's kind of talking about a number of these different things. We talked about particle spacing. We talked about molecules. I hinted at ion size. Carbonate, the ion, is definitely much larger than copper 2, the ion, because it's a polyatomic ion, like a little mini molecule. But also notice that in the top picture up here, the sodium ion is smaller than the chloride ion, which is much bigger. And this is because of the fact that the chloride ion, let's look at a periodic table quick. The chloride ion, Cl1-, has 18 electrons, and the sodium ion, Na1+, has 10 electrons. And so it's automatically a whole energy level smaller than the chloride ion. And so as we're looking at this, this will be important, as you want to think relative sizes. And we'll talk more about those sizes, but I want you to just think about everything that should be included. Okay, so this should all be new to you to be thinking about these things, and it's very important that you're thinking through this. All right, so let's apply this just a little bit. You already took some notes about physical and chemical changes, and now we've talked through some information about particle drawings. So let's do a couple of questions that apply this. If you'd like, you can stop the video and try these two, and then restart the video to see what you're doing and see if you were correct. So the first one, if you stopped and restarted now, the first one wants to know if it's a chemical or a physical change. So remember that a chemical change means that we have new substances formed. Either we have elements formed that used to be compounds, or we have compounds that are now new compounds, etc. So if it's a chemical change, we have new substances. So notice that in here we have this, which is a small compound, and we have this, which is an atomic element. Okay, I know this because there are two different atoms in this small compound, and so that I know it's not just a diatomic element, it is definitely a small compound. In this over here, I have a diatomic element, and I know that because they're both the same color. And then I have this as an atomic element, but it's a different atomic element than it was before we began this reaction. So this is definitely a chemical change. And if you were looking at this as a type of reaction, it's probably a single replacement reaction or a redox reaction at this point. Okay, so definitely we want to be thinking about that. That may not be the case, but that would be one option. All right, so let's look at the second example. In this case, we have this, which is probably a solid. It's at the bottom of the container. It's not filling the sides of the container. This would be another thing that in a liquid, we would look for it to fill the shape of the container. So since it's not filling the shape of the container, this is a solid. This is the same atoms. So now we have as a gas. So this is definitely a physical change. This is just the process of sublimation, going from a solid to a gas without going through the liquid phase. So these are some things that you can definitely draw in your notes as examples, and you can definitely think about ways that you would represent them. Okay, so now we're going to apply physical and chemical changes in word form rather than in particle drawings. So I actually would like you to stop the video here and answer each of these questions, copy them into your learning targets as examples, and then restart the video when you're finished. All right, so let's talk about this. Hopefully you've done this on your own and you're really taking advantage of the fact that you can do that pretty quickly. These should be pretty quick questions. So this is finding out if it's a physical change or a chemical change. So we have iodine vapor appearing when solid iodine is warmed, and this would just be a physical change. This is a state of matter change. We have gasoline fumes ignited. This is a key word because ignition is going to be the activation energy for a chemical reaction. This is different than just warming or heating. This is beginning the part of a chemical reaction. And of course, so what's happening is this is the beginning of the combustion reaction that occurs inside your car engine. And so this is a chemical change. The products will no longer be gasoline and oxygen. They will be new products, carbon monoxide and water vapor. A scab forms over an open cut. And the AP exam doesn't typically ask you about biology-related things. So if you're not sure about how scabs form, they are not just like cells that are blood cells or whatever that are actually forming or pulling themselves together. So a scab, I'm going to guess, is a chemical change. If you look it up, I did not go look it up, but if you look it up, it could be just the fibers are conglomerating together from in your bloodstream. But if that's the case, then it would be physical. But I'm feeling like this is those blood cells are also changing. The chemicals that are there are also changing to help form that scab. Okay, now we want to know if this is a physical or a chemical change again. So let's look. Clouds forming, this is just condensation. So this is a physical change. And milk turning sour, this is now new compounds. This is the fermentation basically, or the same idea as fermentation of the compounds in your milk. And so this is definitely a chemical change. And butter melting, melting is just a state of matter change. So this is physical. So hopefully you were successful with those. If you need help with that, make sure that you make some notes to yourself and ask. All right, finally, the last thing that I want to talk about here are two more things: potential energy and kinetic energy, because sometimes this can be confusing. And then finally, theory versus law, and a little bit about experimentation and how it shows up in the AP Chemistry exam. So we talk about chemical potential and kinetic energy. So we could also talk about like a ball sitting at the top of a hill, having lots of potential energy, and then as it's rolling down the hill, having kinetic energy. But we're not really talking about that kind of thing in chemistry. That's more of a physics example. So what we're looking at here is the idea that we have potential energy coming from the position of the particles relative to each other and their interactions with each other. So these would be attractions and repulsions. And the distance between them actually is, the position is basically the distance between them. And so if two particles are really attracted to each other and their distance is far, far apart, then that would be like if you let go of them, they would pull toward each other, right? So if you have particles that are attracted to each other that are pulled apart to a certain distance, if you pull them too far, they're no longer attracted. But if you have attractive particles that are pulled a little bit away from each other, when you let go, they'll pull back together. That means that they have a high amount of potential energy. The same thing would happen if you have repulsive particles that you force toward each other. As they get closer and closer and closer, it gets harder to force them toward each other. And if you let go, they're going to spring back apart. That would be potential energy. So substances that are in this situation are what we would consider to be less stable. And so less stable substances have high potential energy. Low potential energy is the state that's a really good state. So low potential energy is a much more stable situation. And then, of course, the motion is caused by the formation or the pulling toward each other when you let go, or the pushing away from each other when you let go, or if the formation of the reaction products actually does some work for you, like moving the pistons, etc. So this is how we use these in chemistry, and you may want to spend a little bit more time thinking about this. It's kind of confusing. Finally, the last thing that I want to look at with you, you already know the scientific method from science class from first grade on. However, the things that I want you to think about is that you will be using the scientific thought process when you're looking at variables and constants as you explain comparisons. So you may be saying the ion charge and the ion size will decide how strongly those ions are attracted to each other. So you want to look for what's the same, like maybe the ions are the same relative size or very close to each other in size, but the charge is different and the charge is larger. And then you have to talk about why it matters. So you would use Coulomb's law, and you would talk about how the greater charge, when the size is the same, creates a greater force of attraction. So you definitely want to be thinking along the idea of keep your variables one variable changing at a time so that you can explain why the change that's occurring occurs. You know that that's why it occurs. So this is really important as you practice explaining. All right, so that's your first lecture. You definitely want to make sure that you have added to your notes and that you are making notes in the margin of things that you might need to discuss during class that first week. And welcome to AP Chemistry and to your summer assignment. I look forward to seeing you in the fall.